Hello everyone, I'm Tolga. Today I will present our work Scaling Aware Data Selection for End-to-End Autonomous Driving Systems. Today's physical AI systems like self-driving cars face a massive data challenge. Using it all is too costly and random selection wastes the potential. This necessitates to develop a principled data selection policy such that the performance is maximized under a given data selection budget. In physical AI systems, this problem is challenging for three reasons. First, physical AI systems are evaluated on multiple competing objectives, such as collision avoidance and trajectory progress. Second, the data does not naturally contain well-defined domains or clusters, and different segments of the data may affect these metrics differently. Third, these effects scale differently. Some domains give fast early improvement but saturate, while others improve more slowly but remain useful at larger budgets. Taking these factors into consideration, we need to answer, given a data selection budget, from which cluster should we sample and how much should we take. To address this, we propose Mosaic mixture optimization via scaling-aware iterative data collection, which has three stages. First, we cluster the data pool to identify groups with shared characteristics. Then, within each cluster, we rank the samples using an importance score. Second, we estimate how each cluster scales. For this, we run small pilot experiments by adding different number of samples from each cluster and measuring the resulting performance gain. Then we fit a scaling curve that captures saturation in the performance gain. Third, we use these scaling curves for iterative data selection. At each step, Mosaic estimates the marginal gain of adding one more sample from each cluster. It then selects the next sample from the cluster with the highest marginal gain. As the budget grows, the selected cluster can change. A cluster that is useful early may saturate, while another cluster may become more valuable later. The core idea is that Mosaic builds a budget-dependent data mixture using scaling-aware marginal gains. In the experiments, we use two training pools, OpenScene and NavTrain. The planner is Hydra MDP. We evaluate it on NavTest using EPDMS metric. We compare Mosaic against four methods: random expansion, uncertainty-based selection, Corset, and Chameleon. For Mosaic and Chameleon, the data pool is clustered by geolocation unless stated otherwise. On OpenScene, Mosaic consistently achieves the best EPDMS across data budgets. Compared to random, Mosaic learns much faster, and compared to stronger selection methods like Corset and Chameleon, it still provides clear sample efficiency gains. We observe a similar trend on NavTrain. This is a more challenging setting, but Mosaic again gives the strongest performance across budgets. And it matches full training performance while requiring 42% less data. Next, to understand the internal dynamics of Mosaic, we visualize the selected clusters over 4,000 sample selection iterations in the OpenScene experiment. At small budgets, Mosaic prioritizes Boston and Singapore, which provide strong early gains according to the fitted scaling curves. As the budget increases, the allocation changes. Notice that Mosaic selects more samples from Pittsburgh, which provides steadier gains at larger budgets, and Las Vegas becomes competitive later. This confirms that the optimal mixture is budget-dependent, and Mosaic adapts the allocation as the marginal gains change. We also test robustness of Mosaic under different clustering. For this, we generate captions for NavTrain clips using Qwen 2.5 VLM, and we form 6 semantic clusters using TF-IDF features. Mosaic remains the best performing method, showing that it's robust when the clustering captures meaningful structure in the data. We then update clustering and ranking components of Mosaic. The full Mosaic pipeline performs best overall. Ranking is especially useful in the small data regime, where selecting the best individual samples matters the most, and at larger budgets, clustering and scaling-aware allocation become more important. Finally, we evaluate whether Mosaic also brings computation efficiency. Recall that Mosaic requires pilot scaling runs, which introduce initial compute overhead. However, this overhead is offset by the sample efficiency gains at larger data budgets. We identify two limitations of Mosaic. First, Mosaic depends on meaningful clusters, otherwise it might produce suboptimal mixture. Second, Mosaic requires upfront compute for pilot scaling runs. However, as shown, this cost is amortized at larger budgets. To conclude, Mosaic combines clustering, ranking, and scaling-aware modeling for data selection in end-to-end autonomous driving. Across various experiments, it improves both performance and sample efficiency, and overall, we believe that our method offers a principled blueprint for selecting the influential data in large-scale, heterogeneous learning systems.